Thank you, Agent. Good morning, good afternoon, good evening, everybody. Today, in this short presentation, we would like to show you how MSC Apex have evolved and it is ready for handling large fabricated structure. We have come a long way in the Apex journey. We have introduced CAD to Mesh tool in early 2014, predominantly for modeling, and during which all of you have seen how powerful it is, in particular to create mid-surface modeling of complex geometry. As and when the modeler became mature, we started introducing Apex as a structural analysis system tool. And we started introducing that one in early 2016. As of today, we can handle linear statics, linear dynamics, linear buckling simulations in Apex. We will continue our journey to make sure Apex will be an extensible and fully integrated platform for the future of CAE. At that time, you should be able to handle multi-physics problems all within MSC Apex. Where are we in our journey? We are introducing Grizzly as we speak, sometime this week or next week. In that one, we're introducing the new simulation capabilities, which is linear buckling, in addition to linear statics and linear dynamics. And as always, there will be a continuous enhancement in the modeling and meshing capabilities to support the simulations. What do we have in Grizzly today? We are introducing a lot of new capabilities, such as you mentioned, linear buckling simulation capabilities, custom defeaturing, X-meshing, and to explore the results of any simulation, one would be interested to look at what is the cross-section forces in any given cross-section of the model, and also what are the forces going through the connectors, so that one can look at whether the design is optimal or should we really look at modifying the load path, etc. And today we should be able to do all those things in Grizzly. We have continuous enhancements in the existing capabilities. In particular, edge die connection is a must-have tool for large welded structures, and section view to handle a lot of properties that one would have in the large fabricated structures. So with the inclusion of a lot of new capabilities in Grizzly and with the continuous enhancements in the existing tools, we believe today MSC Apex is ready for handling the large welded structures such as ship hulls, cranes, heavy machineries, etc. Why Apex? And why we think MSC Apex is the tool of choice for handling such humongous structures? What may be the problems in the existing tools? As you have identified, here are the following problems. The problem number one, the traditional CAE systems are too complicated. As you know, to conduct any particular simulation, one may have to use very many tools. For example, a tool for pre-processing, a tool for running the simulation, a tool for post-processing, and sometimes a custom tool to look at some results. And one has to learn very many tools, and hence it is quite complicated. And secondly, for such a large structure where there are thousands of parts and sub-assemblies, it is very complicated to build the FEM models that can provide the results, useful results, quick. Number three, the current CAE systems are parts and assembly agnostics. What does it mean? Once you build a simulation model, it becomes a single monolithic flat structure, thereby it loses the original product structure. The problem number three itself cascades into problem four. Because it becomes a one monolithic flat structure, it is very difficult to make any design changes because the original product structure is lost and the assembly is lost. Don't even know what is the part and where that part in that assembly and what modification one can do. Ultimately, you end up doing the repeated tasks and leading into very expensive. And these are the problems that we identified, and there could be many other problems. Now let us see how MSC Apex today can provide a solution for each of these problems. First of all, MSC Apex is a modern and it is easy to learn and easy to use. It is very intuitive and very natural. It is a parts and assembly based system, meaning once you bring in any CAD assembly model into Apex, it maintains the product structure throughout the simulation process. We have a built-in direct modeling and meshing engine, meaning one can modify the design without leaving the system, or one can use the direct modeling techniques even to clean up the geometry. And direct modeling and meshing is generative, meaning anytime you make any design changes, the system automatically updates every other dependent attribute that is defined on the model because of generative nature of the system. And Apex is a computational parts-based system. That means one can incrementally build the model, incrementally validate the model, assemble the model, and finally assemble a system. And this is made possible because of the integrated solver that's inside Apex. Whether you are a novice engineer or an expert analyst, you always have a problem or a question in your mind, why my simulation did not run through. Today in Apex, we have built-in tool called Analysis, Readiness, and Remedy that will find where the source of problem is and inform the user, and not only inform, it also suggests the possible remedies. And in Apex, that every tool comes up with a what is called online contextual video documentation. If you would like to know what the tool does or how the tool works, it's only a couple of clicks away to get to know through the video documentation. Let's take a look at the demo of these features in Apex. All right. Here is one of the, not a simple model, a quite complex, a shipyard crane model, half the model. And when we import the geometry, it maintains the product structure, as you can see here. Now, this is the layout of the GUI. Then how do I understand what these tools implies? If you go to the help and introduction card, quickly it takes you through what each of these tools does. And quickly you should be able to understand and navigate through the system. And the help document will take you through each and every functionality of the modeler or the structure of Apex. For example, if I go to the modeler and tools and maybe the loan subordinate condition and maybe enforced motion, and it will take you through how to define the enforced motion, for example, and here is the documentation for that one. And more importantly, you can take you to the movie which explains what exactly this tool is all about.
So from loads and constraints, I'll select
and it is that easy to understand, to navigate through the system. Not only that, you need to go through with the built-in documentation, and there is an online context help. For example, for the enforced motion, if you hover over on the tool, and here is the video that take you to the same location where we navigated through. That means online, contextually, you can find where these documentations are. Okay? So it is that easy to navigate through the system. Sorry about that. So let's look at this system. Let's take a look at one of the subassembly in this model. Let's take a look at what's inside this model. As you can see, It's made of very many parts, and let's navigate through one other part. Show only. And is this part is ready for meshing and assembly. And if you look at the details of this part, now as an user, one may make certain decisions. Let's say I would like to increase the thickness of this part, and I could use what is called the push-pull tool, in which I simply select the face and drag that one to increase the thickness. For example, we made the thickness almost 50 millimeter thick, right? And under defeature tool, now if I would like to delete some of these fillets that is unwanted in the geometry for the simulation purpose, can I delete them? I defeature them. It is as simple as that. Can I remove this notch using this push-pull tool? I can simply take that one and extend that to that and deletes that notch. Can I make some design changes? For example, if I would like to reduce the size of this hole, and now I can take the face, and right now that diameter is about 150. If I make it to 300, now you see how the geometry gets modified. Likewise, if I want to make it kind of symmetric, let's make the change that easy. So that's how the direct modeler that's built inside Apex will let you clean the geometry, at the same time modify the geometry. Now let's take a look at how quickly we can create the mid surface for this part. And there are very many tools in Apex that helps you to create mid surface of any complex geometry. In this case, of course, it is a constant thickness part. Let's go through that tool to find the mid surface geometry of this part. And we got the mid surface geometry. And can I mesh this part? Let's go through some meshing tool. And let's create a mesh for this part with, for example, 50 millimeter element size. And note that these structures are so huge, and this particular model is about 20 meters in long. And the normal element size that I might use is about 100 millimeters. And as you see here, even the inside bracket, I kind of made it as 50 millimeter. Right? Now, I can expand that one, which is my auxiliary girder, which is the subassembly. As you can see, it has hundreds of parts. And now, can I navigate to the location where is this particular part? And that is this particular part. And now, let's see if I can connect this part to the rest of the parts in that particular subassembly. Okay. So this is that's a particular subassembly, and I have created the mid surface geometry for that part. Let's go ahead and mesh that part. In this case, let's make it as maybe 100 millimeter and create a mesh. Okay, it's created a beautiful mesh for the particular part. Now let's go ahead and extract the thickness for this part from the solids. Auto thickness extraction for this part, and this is the mid surface geometry, and the associated solid I'm going to select so that I can extract mid surface geometry for all those parts based on the original solids. So it's as simple as creating the mesh and extracting the thickness from the original solid geometry. And now, if you notice here, that's the inside baffle wall that we created a mesh. Now, how can I connect this part to the rest of the part? And we have two techniques in Apex today, in addition to many other connections one can create. For a large welded structure, either you can create the glue or you can tie connection. Let's try both of them in these examples. Let's create a glue between these two parts, and these parts are massive structures, and as you saw, the thickness of the part is in the order of maybe an inch or two, and hence I'm giving a kind of big tolerance to create the glue between these parts. Let's go ahead and create a glue. And as you see now, that green part, which is a baffle wall, got connected to the structure here. All right, so now we have assembled this part. Then how do I validate this model? Or how do I really validate this particular subassembly inside this one? And here is a tool that we are going to set to run the context of a simulation. When I set that one, and what we see on the bottom, what is called analysis interface panel that navigate through to see what are the issues in this model before it can run, or what do we need to do. For example, here, we would like to run maybe a linear static analysis for this one. Obviously, it's identifying, since you set the context to run a static analysis, you have not defined the constraint, you have not defined the loads, now you have defined the material. That's exactly giving you a guide that you need to fix those three problems. And let's go ahead and create a material and assign to this part. And let's take steel material. And assign that material to these parts. Now, if you notice, as and when I complete a task and that red was identified as an error, got cleared. And material is assigned. Now, we need to create the loads and constraint for this part. Let's go ahead and create a constraint, and maybe constraint on these ends where it is connected to the rest of the system. At this point in time, we are going to analyze just for this model itself of this assembly. We'll constrain those two, and let's apply some kind of pressure load on the top of the skin. And let's say I would like to apply maybe 0.1 megapascal on that face of the model, and as well as that face of the model. And note that we are operating all these things on the geometry. As and when I apply the things on the geometry, anything associated with the geometry gets automatically updated, right? And now if you see here, now there are no red color indicating there are no issues in the model, and now it is ready to run. So let's click on this running man, which is running this particular problem with the integrated solver. So as you saw here, it is that easy to go through the system to create an assembly, a subassembly of this assembly to validate at a subassembly level. And as it completes the simulation, let's take a look at how we can explore the results and whether this particular subassembly is ready to be assembled with the rest of the model. And it ran through. Now let's look at the results exploration. All right, so I'm going to change just the scale of displacement and toggle through, looking at the behavior of this subassembly inside the big assembly of this model. And you can navigate through looking at different components of the stressors, the displacement, and whatever. It is that easy to walk through in the system, and that's the reason why we believe now with the integrated solver and computational parts-based system, assembly architecture will let you do this kind of simulation with ease. So we have done the linear static analysis. If I would like to conduct a buckling simulation for the same subsystem, and is that easy? I can simply go and set the context of the same subassembly. Now I can toggle, instead of static analysis, to buckling analysis. Now the model is ready to run the buckling simulation, and there are no other errors associated in the model when we change the context to buckling. Let us quickly run even the buckling simulation. So this is the reason why we are promoting that Apex is ready for running this kind of simulation very intuitively and very elegantly and very easily in Apex. And let's take a quick look at the results when it is done with the buckling simulation. It takes generally about 30 seconds or less. All right, pretty much it is done. Now, the results exploration is very common user experience. Now, I can quickly look at what are the buckling behavior, and the first buckling mode is somewhere here. And obviously, this particular buckling mode is a spurious one because this part of the model should be connected to the rest of the model. That's the reason it is behaving that way. And the realistic buckling mode, probably in mode number 5, not even that, probably mode number 6. Now you can see that seems to be the realistic buckling mode that's happening in the system, right? And maybe you can just reduce the scale of animation, and you can browse through what are the different buckling modes this subassembly experiences, and now what are the critical buckling loads. It is easy to look at the buckling loads, and as you see here, now we saw the first 4 modes are the spurious modes, and the first mode, probably mode number 5, is the buckling mode. And if I change the scale factor to, let's say, in this case, I'm going to say 5. That means 5 times the load that is applied in this case. By then, the first 4 modes are going to be a critical. And of course, the first 4 modes are not the realistic mode. Let's take a look at the changing the scale factor to 6. That means the 6, 7, 8, at 6 times the load that is applied, this structure is going to buckle. It is that easy to navigate through looking at the buckling behavior of the system. So we went through how easy it is to set the model, run the simulation, and investigate the behavior of the system, and everything at a click of a user's button, right? And as you saw here, we have done investigating one subassembly, and pretty much we can go through all the other subassemblies similarly, and then finally we can assemble this model to run the entire system. So we have seen how easy it is to use. Now let's take a look at how we can use this system for much bigger, large fabricated system. Let's take a look at that one. Here is a ship hull model, which is a large CAD model, and which is about 120 feet by 75 feet of this model, and about 4,000 parts. That is still half the structure, and 175 by 75, and there is another half probably in this model, right? And typically today, this would take probably a couple of weeks to build the model, and maybe a couple of weeks after that one to run the simulation in an existing system. Whereas in Apex today, this can be done in less than 2 days with all the tools that we have seen in the previous example. In Apex, we believe in what is called divide and conquer. That means because of the computational parts-based system, we can incrementally build, incrementally validate each subsystem, then assemble, and then run the simulation as an assembly as a whole. And can we really do this big model live? And let's take a look at it. Not that one. All right. Here is that one section of the hull with about thousands of parts, and these are the different subassemblies like a floor deck and 4 aft girders, back panel, and mainframe, etc. And now I'm just copying one of this model just to show how we can incrementally build and validate this model. As you can see here, it's made out of many parts and has what is called the keyholes, or somebody may call dog holes or whatever, and there are tons and tons of them. And how do we really de-feature those things in Apex? The process in Apex is quite simple. Let's go through first creating mid-surface geometry for all these parts, and let's use the constant thickness approach, and let's create mid-surface for all these parts. Okay, and it created maybe multiple parts and assigning different thicknesses. All right, and now let me change to auto color, and you can see here there are many of these kind of keyholes, and we have introduced what is called custom defeaturing based on pattern recognition to defeature many of these kind of geometry. And under defeature, we have custom defeature. Basically, you select a pattern, identify a pattern, and define some tolerance to the pattern. And maybe I'm just introducing about 80% of the length tolerance and 10 degrees with respect to the angle tolerance. That means within that variation, once we identify one of them, and we'll try to search all those similar patterns in the model. Let's say, and now I'm going to select one of this pattern here, keyhole. All right, and then I'm going to select in the entire model how many of such things are there. And it found 106 such features of keyholes in this model. Now can I defeature them? And it's as simple as that one to delete all those keyholes. And probably this shape is a little different. Let's take a look at that one. And let's see how many of that kind of features are there in this model. And there are 8 of such things, and defeature them. And those are the kind of non-standard features. And in this model, there could be standard features as well, and such as this fillet. And can this tool work on these standard features also? Let's select one of them, and let's identify how many of them are there in this model. And there are 123 features that identified the fillets in this model, and now you can say go on defeature. So now it's as simple as passing through these techniques to really defeature that one, to remove the unwanted geometry that is not suitable for creating the meshed model. All right, so here are the 2 parts here. And now, because of these parts having a various thickness, and because we created mid-surface geometry, all these plates are not necessarily aligned in a plane. And so that we cannot, when we need to extend all of them, we need to bring them into a single plane, and that can be done using this tool, what is called auto up to alignment. And before that, let's get rid of some of these extra vertices in the model. That is done. And use up to alignment. Basically, I'm selecting all these surfaces. Then I'm going to select one of these as a reference surface to which it's going to align. That means all the 13 bodies or the surfaces offsetted with respect to that one reference geometry. Now we should be able to extend all these parts. Let's take a look at extend all the surfaces. And again, I'm going to use about an inch as a tolerance, and maybe about 5 millimeters as a cleanup tolerance. And I'm going to extend all these bodies to kind of touch each other. Okay, all the parts are extended together now. Now we can go and mesh this part. Surface mesh, let's use maybe 100 millimeter in this case, and create a mesh, and mesh is done. And let's quickly look at if there are any invalid elements that does not pass the simulation. When I click on that one, you see that there are no invalid elements. That means this mesh quality is good to run through the solver. All right. Now, these are all individual parts, and now we need to assemble them together. Again, as we mentioned, we could use either the glue techniques or an edge tie. Right? Let's try the edge tie technique of connecting all these parts, and I'm going to use a cleanup tolerance as 5 millimeters. That means when these edges are tied together, and within the tolerance of 5 millimeters, if it creates any sliver elements, it automatically deletes them. Now, it's as simple as select all the bodies that is to be tied together, and all the edges that is touching each other are going to be tied. What is the powerful feature of this particular edge tie? Right now, it created the congruent mesh. At the same time, it maintains the original product structure. And this is what is unique in the industry, so that we can maintain the product structure, yet we have the congruent mesh between these parts. And now, is this ready to run? And is this a validated model so that we can assemble with the rest of the parts? Let's set the context of that subassembly to validate this model, and we can run this one to validate by conducting the normal modes analysis. And as we set this to run normal modes analysis, it's saying that one it is missing material. Now let's go ahead and create a material and assign the material to these parts. Right? Again, I created a steel material assigned to all these parts. So now if you see here, everything is clear. Now it is ready to run. And let's click the running man to run the normal modes analysis. So what you saw here, we selected one of the subassemblies in the model. It is not one part. It is many parts constituting that frame. And we created a mid-surface, and we connected those parts with an edge tie connection. And we are running the simulation to see whether this particular subassembly is ready to be assembled with the rest of the model. Right? So it's just about done. And now let's take a quick look at whether that part behavior is ready to be assembled. And the post-processing tool, to look at the behavior of this one, basically we are looking at whether the normal modes behavior ensures that the parts are intact and the overall behavior seems to be good. And looking at starting from the first rigid body modes, are the first mode is 7th mode, and you can kind of navigate through to see whether this part is good to go. It's as simple as that one to validate the subassembly, right? So we're done through this subassembly. Now, is that easy to build a model of this humongous structure? Let me just delete this one. The reason I'm deleting this, I just copied one of the same model from the other part of the model just to run through as a incremental validation of that one particular model. Now here, this consists of many subassemblies. Let's go through one at a time. Let's see, this is the main frame and made out of maybe 3 subassemblies, and each subassembly consists of many parts, right? And now let's go ahead and create a mesh. And in this case, I'm going to make it as kind of pretty big model and big element size so that we can run interactively. And mind you that many of these structures will have much bigger element size, sometimes maybe a 1 meter element size. And 300 millimeter is reasonable for this one, that what as I can see. And let's go ahead and mesh that part. So meshing is done. And the next step is to extract the thickness for all these parts from the solid model. And I'm going to associate the solid geometry from which it's going to extract the thicknesses. And right now here we have 3 subassemblies of that main frame, maybe made up of maybe hundreds of parts in each frame. And now it's looking at the meshed model and the mid-surface model and the original 3D geometry from which it is extracting the thicknesses. And also it's going to group to minimize the number of properties it creates with a tolerance of 1 millimeter. And user can use their choice and up to what tolerance of the thickness they would like to merge so that they can create a minimum number of properties, right? And it should be done in a minute. Yes, it is done. And there is 16 millimeter is the maximum thickness in one of these parts. All right. So one subassembly is done. Let's take a look at maybe the floor decks. Show only. And here is the floor deck model, and consists of many stiffness or the beams, right? And let's take a look at creating the mesh for this one. And here also, for the time being, I'm going to use to mesh all these parts also as shell element with 300 millimeter, and I'm going to extract the thickness for all these parts from the original solid model of this subassembly. Again, so as you can see here, we are navigating through the different subsystems, subassemblies of this big system, right? So now we have done this second subassembly, and there are two more to go. Let's take a look at the back panel as yet another subassembly, and let's go ahead and complete this mesh as well. 300 millimeter and thickness, same steps. And as you can see, once you know the tool, it's kind of a very unique, very identical steps for each of those subassemblies, right? So now we are extracting the thickness for the back panel of that model, and once that is done, and there is one more subassembly, what is called 4F girders, and let's go ahead and finish that model as well. And as you can see here, this is what we call divide and conquer. That means we walk through the model, identify the subsystems, and each subsystems we validate one at a time, and then we assemble for the big model. All right. Now, the last subassembly in this one is 4F girders and mesh. Only the bit surface mesh and thickness extraction for all these. From the solids. So by now, pretty much all the parts of this model, maybe about thousands of parts, right, has been bit surfaced, meshed, and thicknesses have been extracted from the original solid geometry. And as an end user, I could go through validating each of these subassemblies. So that's what it would have taken for me to complete this model, maybe a day or two. But now probably we can finish this entire model in about an hour to show the demo of this complex assembly. Okay, so once we have meshed all these parts, what is next? And here is the meshed model of all those subassemblies. And now let's go ahead and connect all these parts. And like we mentioned, we could either glue or we can use edge tie. And you saw the edge tie for one of those subassemblies. Now let's use glue to glue all these parts together. And I'm going to use a tolerance of 30 millimeter. Approximately there is a gap between many parts in this model. And let's go ahead and create glue for all the parts in this model. And the system is searching all the parts in this model in the subassemblies with the tolerance of 30 millimeter, and then it is mathematically connecting the glue between those parts. And could we have used the edge tie? It is as simple as that what we've shown in one of those subassemblies. And in any of such models, you could selectively use tie in some of the areas, and you can selectively use glue in some other areas, so that an assembled model will have a combination of glue and tie. A choice is yours, and depending on what is your objective and what you are trying to achieve, and whether you are interested in looking at some areas that you would like to have a common noded model, and hence you would like to create a tie, right? And you can do many of those things. And in this particular model, and when I kind of visualize this one, and of course it was not that easy, but I know that in one of the part there is a bigger gap. That's the reason if you see between this cross member and this floor, and there is no glue, and there is one missing glue. And what I'm going to do, I'm just going to create that particular one manually, because the gap between those two is little bigger than 25 millimeter, right? Now it's going to update the glue, and if I look at the glue between that one, Now that's connected. All right. Now I believe all the parts in this model are assembled using glue. So what is next? Next thing is to apply the loads and boundary condition for this model so that we can run a simulation. And in this model, and what I'm going to do is to apply some kind of pressure load on each of those floors and then kind of constrain the rest of the models, right? Depending on how this model is connected to the rest of the model or how the overall boundary condition is created. So now in Apex, we do have what is called the macro record and replay. And I just use the macro on the same model to apply loads and boundary condition. I'm going to replay that macro so that I can apply the loads and boundary condition on this model, right? So those are the areas that is constrained, and those are the floors on which we apply the kind of pressure load. So now this model is just about ready. We assemble the model, we apply the loads and boundary condition. Now let's the context to run a simulation to see and whether it is ready to run as a whole, right? Let's take a look at that. And as we are setting a context, now there is still red color, meaning there is a missing material for the parts. We did not assign the material for the entire model. Let's go ahead and select that material, that what we created, and assign that material to all the parts. Okay, as we assign the material and that is gone, and there is invalid element quality. Somewhere the model is not ready to run because some element is invalid. And how do I find that one? And how can I fix that one? Right? And invalid element quality, when I double click that one, in the entire model there is only one element that is failing the quality criteria. And how can I find that one element in this big model, and how can I fix that one? And it is a quality tool. When I click on that one, it's showing that this one element which is invalid, and let me go and isolate and find where is that one. Now I can click on this zoom. When you click on that one, it will take you to that element, and this particular element is tapered. That's the reason it is failing the simulation. That means we checked every entire model with the built-in solver to make sure is it ready to run. Now can I fix this? I'm going to use the edge and vertex tool now basically to correct that one. And as and when I do this edge and vertex drag, I drag those vertices together so that that element got corrected. Now as you can see here, the model is completely ready to run, right? And we see no red color, and this is ready to run. And of course, now I need to set this to static analysis. And since I'm going to set this back to static analysis, I would rather make sure I set this context once again. That is, with respect to static analysis, it has no other errors or warnings that we need to take care. And if you come back and see, it is ready to run. All right, now let's run this model, which may take about 3 to 3.5 minutes. And meanwhile, let's look at what are the other tools that we have in this Apex that helps to build such humongous model. Okay, MSC Apex provides, since it is running, kind of jump back to so we do have what is called industry-specific modeling tool, in particular for this kind of a ship hull structures. And most of these stiffener beams are traditionally modeled with beam elements, and there may be many reasons why it is, and sometimes even the certification process dictates those things to be modeled with the beam elements. But in this day and age, with the advance of computers, and we should be able to take advantage of the fast computers so that we can do many things at a time. And even if you would like to model this as a beam element, And we do have the tool what is called creation of beams, very exotic tool what is called shape and span. That means you can create a shape inside the tool and you can assign that one to a span. And then graphically you should be able to visualize whether the orientation of this beam is proper or not. Then you can modify the orientation of the beam and modify even the offsets, right? And let's say originally this was an L-shaped beam. Now I would like to replace that one maybe by a I section. It is as easy as creating a shape and replacing that span with a new shape, right? That's what we have a tool that helps to build such models. And in this case, there are hundreds of stiffeners. And once you create the beam elements for those stiffeners, and now we can go and tie those beams with the floor, this implies that the product structure maintained, yet creating the congruency between the beam elements as well as the shell element representing the floor. It is that simple. And secondly, if we create beam elements, if some area of interest that I would like to create a detailed meshed model, then because of our parts and assembly architecture, that we maintain the parts as the original product structure, we can go and identify the area of interest and we can isolate that model by slicing that model. And then we can create a detailed, maybe a 3D hex mesh model or a tet mesh model and 2D shell mesh model, including the beam model in that, the 2D shell mesh model, and now we can glue that detailed mesh to the rest of the model, what we call global local modeling techniques. And because we have the glue and its integrated solver, it will ensure there is a connectivity between the fine mesh and the coarse mesh in the full assembled model. Those are the tools that makes the life easier and simpler to handle such large structures. Let's take a look at if it has run through. All right, simulation is done, right? Now let's go ahead and explore the results. Okay, all right. Now let me make the scale of displacement maybe 4 millimeter and the stresses and animate. Okay, now if you see here, probably the high stress is about 1.5 e power 3. Let me just set it to 400 and lock that one. And now we can kind of slice and dice the model to understand the kind of overall behavior. Which part of the model is highly stressed? Where is the deformation is high or whatever? Now, can we quickly look at where are the hot spots, right? When I toggle this one, and it's taking us through where are the hot spots, high stresses in this model. And obviously, those are all in those beams and which are bending too much. And also, can I look at the displacements? If you look at here, there is about 55 millimeter displacement in this span. And what it implies that there is too much of sag here, and this is fine. That means as a part-based system, we're able to do all these things. The question is now, can Apex provide us some kind of design alternative? Can I quickly look at what can I do to improve the design? And can we do those kind of things in Apex? Sure, yes. And what we can do, we can take a look at this one now. Let's say I would like to create one of those frames and copy that one, maybe a couple of frames, and add that one into the original structure. And how easy it is to do that one? And I can go back to my product structure. Let's look at maybe only those frames. In that one, I will look at only the middle frame, or whichever. I can keep only that one. And now I can select the entire frame consists of the original geometry, mid-surface geometry, and mesh model. And let's do that transformation of that model by copying the entire frame and move that one for about 1.5 meters. Right? So that's one. And now we can copy as many as you want, and we can reload. All right, so we created a frame and extracted thickness for that one, and now that's what you're seeing here. All right, and let's go ahead and create the glue for those parts, and we just added one frame. All right, now I'm going to bring the floor beams and the girders, which that cross section is going to be connected, right? And the back panel is not going to touch that one. Now we can go ahead and create the glue between the newly created frame and rest of the structure. I'm going to select that local area only and update the glue. I could have selected the entire model blindly, but it would take more time, and why would we do that one? Or I could have selected only the area of that model and the rest of the model locally, I could have connected that one. So the system allows you to do whatever you feel comfortable. So right now what it is doing, it is connecting that frame back to the floor as well as the fore aft girders wherever it is touching each other, right? And plus, since we box selected many of the glue in the model, and whatever previously created glue, it's going to update all those glue automatically. Okay, so it should be done. That's right. It's now the model is updated, and now I can show all. You can see the new frame that's created here, and glue is updated. Now, if I set the context of that one to see whether the model is intact and is it ready to run. All right. So if you look at here, now we have added this frame and it is ready to run. And maybe I can click the running man to run this modified design. While it is running, let's take a look at PowerPoints. So what did we do? We took the entire model and we parts and assembly, assembled the model, and objective was to make sure that are we getting the right results. And in Apex, that you can ensure if the structure is safe and is it stable by conducting the linear static analysis to see that one the stresses are well below the yield and the buckling behavior is well below the critical buckling. So by looking at those two, now one can calculate the margin of safety, and also we can explore that which part is contributing to that cross section, right? Let's see if the model has run through. It's almost there, 97% done. And once it is done, maybe we can take a look at the results and the effect of the results that modified this frame. Did it improve the performance, right? And that's what our intention here. Here is a model that I ran, and while we are waiting for the run to go through, this is the original model with 3 frames, right? And now in the modified design, in fact, I've added many more frames here, maybe 4 more added to that one. And as you can see here, with the given identical conditions of the result exploration, now we had kind of caving of this floor much more than what you see here. And in this example, we were able to improve by an order of magnitude, 100%. Basically now in the modified design, we have about half the displacement that what you saw here. And as you can see here, even the stress distribution is more uniform compared to what you see in the original model. And this is what we call the rapid design improvements that Apex facilitates. Okay, so simulation is complete. Let's quickly look at what are the results there. All right, so here is the modified design. Let's set the same scale factor for the animation. And now we are looking at the behavior of that entire model, right? And now if you notice here, which used to be 1.5 e power 3 came down to 1 e power 3. Let's set that corresponding to same number. And if you see here, now the colors are more uniform here. And more importantly, can we look at the hotspot to see what are the numbers? And can I look at the maximum deflection under this modified design? Okay, now it is 46 millimeter as it's supposed to be 63 millimeter, whatever. There is a considerable improvement, even just making one frame adding to this. So what have we learned? That Apex is ready for any of these large fabricated structures, such as stationary cranes, like what you are seeing here. And it's also ready for moving cranes. As you see here, that one of the cranes that we have a telescopic zoom, and we were able to articulate the zoom to a different angle and different length and run the simulation. And now, with that example or a case study, we believe that MSC Apex is ready for many of that kind of crane industry. So, it is a system today that's ready for large fabricated structures, and you have seen how easy it is to learn and use, and how the direct modeler helps you to do the modifications to the parts as a design, or you can use that to clean up the geometry. And it is a modern part-based system, as you saw. And whenever you make a change, it automatically updates because of the generated behavior. And because it is an integrated solver, and that helps to validate the model as you build the model. And we have seen how easy it is to set up the static and buckling simulation, and the results exploration, which is quick and easy to look at what are the behavior of the system as a whole, and can we calculate the strength and stability of the structure, and explore the result by looking at the cross-section forces or the connector forces, so that one can make a very intuitive design recommendations. And it also comes up with Python scripting capabilities once you know how to use and where to find what, and the sky is the limit to make any kind of things that what you want using the scripting capabilities. And we believe, as you could see even in this example, that we can do at least 10 times productivity compared to what you are today, maybe even more. Because this model, as you saw, we run live in 1 hour and showing you all the capabilities of Apex and useful features of Apex. With that, we believe that it's ready for handling large fabricated structures. Give it a try. I'm sure that you will like it. With that, thank you all very much.